Trying to get back at it because it turns out this is more like a 3-hour class than a 2-hour class. So we got a bonus hour of learning. Aren't you lucky? But ground rods, generally you're putting this ground rod into the soil. If you're driving it and it doesn't go down, there are rules and procedures for driving it at an angle. And then if it still doesn't go down, digging out like 36 inches down and throwing it horizontally and then covering it back up again is an accepted installation procedure. So generally you're using a ground rod. Although in certain soil types, then where ground rods are not going to be successful, it's better to approach a different grounding methodology and be prepared for it. Ground mount systems, carport systems where you're already putting in foundations, planning on a concrete encased electrode. You can't just use the rebar in the electrode. You have to have 20 feet or more of continuous rebar, which is not normal. And so you need to use not a number 6 or a number 8 grounding electrode, but number 4 when you're putting the ground rod into concrete. The grounding electrode, if you're doing multiple grounding electrodes, like I mentioned that I sometimes do, they have to be greater than 6 feet apart. Otherwise, they don't have the same impact. It's like putting in 1 ground rod instead of 2. For it to be a truly supplemental electrode. So buildings actually have a supplementary electrode, an additional grounding electrode. Often the utility is already putting this down at the utility transformer down by the pole. But if you're, say, doing an off-grid home, you need to put in an additional ground rod. You're required to, in fact, 6 feet away from the existing ground rod. Other than that, you can put in additional grounding components, and it's allowed. You're allowed to put multiple ground rods off the same grounding electrode conductor. It's just not required. So putting in an additional ground rod that is right next to the existing ground rod would just be a redundant backup, but it wouldn't put in any additional actual grounding to the system unless they were spaced 6 feet apart. You still have your main grounding electrode, 1 per building. All right, so we talked about how that grounding electrode conductor, if it's number 6 or larger, it can be run without a cable jacket, without physical protection, unless it's subject to an area where it's likely to be physically damaged, such as alongside a building that's alongside say, carport. If a car could hit it, it needs to be protected. So there are minimum size of grounding electrode conductors, although then there's additional exceptions, so that, say, ground rods, the smallest, even if you're doing a larger service, if you're using a ground rod, you're allowed to go with a number 6 instead of a larger grounding electrode conductor. Sometimes local jurisdictions overrule that, and they'll tell you, no, if you were installing a 400 amp service, we want you to use a number 4 grounding electrode. All right, so now we're talking about the actual ground path. When we say all metal needs to be grounded, if you're taking metal conduit and you're landing it onto a metal box, because you have a metal on metal connection, is that an actual ground path? Or do you need to install a separate ground bar on the box and then have every connection kind of tied into the ground bar to ground the thing? So what are the rules on that? Well, one, if it's a plastic box, well, then you need to continue the ground through the box. And so if you're having metal conduit land on a plastic box, well, then you would install this little ground rod and select fittings that have little ends on them called grounding bushings to connect the ground to the bar, and then continue on through the other side of the box. So using a metal box can sometimes prevent you from having to put that ground bar in the box, but there's special rules for that. These knockouts on these metal boxes can sometimes contain concentric rings. And if you use the inner ring, the inside of this knockout and not the full knockout, this remaining little dimpled piece is considered an impaired connection. And so when you're bringing your conduit into these boxes, you have to use the outer ring on the knockout with traditional coupling and lock nut in order for that to be a grounded connection. If you're using the inner ring on one of these things, then you would need a grounding bushing going on into a ground bar. So, if you're not putting little pigtail grounds onto a ground bar on a metal on metal box, then you have to be using the outer knockout on that box, which means your conduit size and the knockout size have to be the same in order to avoid kind of pigtailing your grounding onto a ground bar. But there are rules to say, the conduit is bonded to the metal box if you're using threaded couplings, wrench-tight connections, and metal boxes and metal raceways. You don't have to use the grounded bushings. But if you're doing an exception to that, then you need to find a ground path for the metal, through the metal, all the way, from the service panel up to the rooftop. If you're not using EMT conduit, if your conduit is plastic and you're using a metal box, well then you would have your ground come out of through the conduit, and then through the conduit out up and through, and then go off and land on the ground bar on the metal, and then continue on the plastic and continue, or just go straight through and use plastic conduit, plastic box, plastic fittings. Now, DC has to be in metal. The equipment ground conductors, what constitutes a ground path? Well, you could just have a ground wire, a ground cable landing on a ground bar. As far as using the metal conduits for a ground path, even short runs of flexible metal conduit for small circuits is an acceptable ground path, but not always. For circuits that are over 20 amps, flexible metal conduit would not constitute a ground path. Does that equipment ground conductor need to be green? It either needs to be bare or green. It can't just be black taped green until it gets to be a number 4 cable size or larger. So if you're using a number 8 ground, then it can't be bare outside a conduit. So it's common to have number 8 green ground wire on a project. When you're upsizing your wire because of voltage drop, you're also upsizing the ground proportionately, unless it's being overruled by an exception that says like, hey, you're using a ground rod anyway, no, we're just gonna keep going with this. Minimum equipment ground conductor size. Well, look, a lot of solar circuits are 20 amp or 40 amp circuits, and it's saying, well, the equipment ground conductor only needs to be number 12 or number 10. The grounding electrode conductor, the drain for the entire system on services that are 20 amp or 60 amp, needs to be a little bit larger than that, number 6, number 8, and the DC side has its own grounding electrode conductor that you need to run up to the rooftop. So sometimes you combine the AC equipment ground conductor with the DC grounding electrode conductor, and you have to use the larger of the two sizes. So just to keep everything straight and clean and code compliant, I'm always running a number 8 ground up to the rooftop, even though it could be smaller than that. Even though with solar, you're often upsizing your wires as well. You don't run into needing to upsize beyond a number 8 up to the rooftop until you get into like commercial solar systems. So here we see that the DC grounding electrode conductor should be no smaller than number 8 and doesn't need to be larger than number 6 when connected to a ground rod. And so to ground the solar rail up on a rooftop, it's common to run just number 6 bare up to the roof, or to do it through the conduit with number 8 green sheathed. Okay, so section 300, wiring methods. So we've established like what brings power into the building, and now we're defining better what carries the power inside the building, and then we'll get into general equipment, and then we'll get into specialty equipment. So thumbing through a code book, the more basic stuff is up front, and it logically expands upon that as you get more and more detailed. But let's say you're trying to run your wires through a house during rough-in and you want to go through some wood members. There's code that says you should be no more than 1.25 inches away from the nearest edge of the wood members. So like on a 2x4 going in through that 4-inch thickness, you have to be kind of towards the center to hit to it, or you put a steel plate whenever you're closer to that. So if someone's driving a lag into, or nail into the rafter to mount something, you have a 1/4 inch and a 1/4 clearance. For that matter, if you're mounting stuff on your walls and going into those studs, being aware of that and not selecting fasteners that are deeper than 1 1/4 inches plus the drywall thickness, 1.5 inches. It's about all you want to select for a fastener that goes into a rafter or into a stud. When you're going underneath the roof decking, you have to be 1.5 inches away from the roof surface so that roofing nails don't drive into the conduit. If you're coming in from underground, there are splices and taps that are for underground cabling that you can find at Home Depot. When you're backfilling it, when you say, okay, well, can I do a direct burial underground cabling run? The answer is yes, but what hurts the cable is if heavy devices on top of that soil compact the soil and press rocks into that cable sheath. And so generally, you can do direct burial cabling, no problem, with big, thick underground, made for direct burial cable. Solar cables, direct burial cable. But if you're going underneath a roadway where you have heavy equipment that's going to be driving over that, you want to put conduit along that roadway to give it a little bit more physical protection. But doing the entire underground run in conduit can actually create more problems than it's worth, in my opinion. Really long underground conduit runs, they're not very good for pulling and repulling and pulling and repulling, nor can you easily pull cable through conduit that has existing cable in it unless it's grossly oversized. So often direct burial cable is the most simple, to the point, cheap, effective wiring technique, and utilities do outside of conduit direct burial cable all the time. Expansion fittings coming between the ground and the box for especially in colder climates for earth movement. Okay, raceways exposed to different temperatures should be sealed. So now it's not just coming into the building, the power supply coming into the building, but the wiring inside the building exposed to 2 different temperature elements should be sealed. We talked about that earlier. Okay, so when you put AC through a metal box, you can get inductive currents into that metal box. So there's spacing requirements that are generally spaced at where the knockouts are to go into that metal box without heating up the box through induction. It's not something you have to worry about for AC, or if you're using the knockouts locations on the boxes. If you're making your own knockout locations on the boxes, then you need to space them apart from each other. Again, we see The only time where you can run conductors in parallel because of ampacity constraints, so if you have one really big cable and you'd rather pull two smaller cables, you have to use 1/0 cable or larger. Just common exam question. Likewise, if you're doing parallel split raceways, the raceways themselves have to have the same characteristics, the same load, the same cable size, the same ground. They have to look kind of identically the same when breaking out a cable into parallel runs. So you can't have all the power cables in one conduit and all the neutral cables in another. They have to be uniform characteristics. So there's ways you can calculate heat dissipation in conductors using engineering calculations, or you can use the fudge factors if you're an electrician, you're not an engineer, and you're not putting your stamp on it. And so there's adjustment factors for when you put more than 3 conductors into the same conduit, because now just the temperature in the conductors, it's enclosed in that conduit. The air can't escape. It's not free air. And so that temperature is staying inside the conduit and it's heating up. And so there has to be less current in bundles of conductors than just conductors where it's just a couple of them, 3 or less. These adjustment factors only apply to certain areas. And so for raceways that are less than 2 feet, so you're at the edge of the array, you want to put all of the cables into one big conductor and throw them into a box. That run is less than 2 feet. If you're going from a gutter into a service panel, you can have a short section of conduit that does not derate the conductors because it's the only point on the system where you have 30 cables going through one big, 2.5 inch pipe. That short section, as long as it's under 2 feet, you don't have to do the adjustment. Underground conductors that are 4 cables or less, if for less than 10 feet. So underground coming up, you don't have to do the ampacity adjustment. Then you have additional adjustments for exposure to sunlight. And this has changed a lot. It used to be like a 1 inch or less, between 1 to 3 inches, and then over 3 inches. Now it's simply, if your cables are within 1 inch of the rooftop, you're going to have to add 60 degrees Fahrenheit to your temperature derating unless you're using incredibly robust cable jacket. And so that's a very harsh addition for temperature. And so it's best to keep your cables, above 1 inch. But if I've had projects before where I'm looking at my upsized number 6 ampacity, and it's like twice as much ampacity as what the solar array would actually provide. And I'm looking at my conduit going across a metal rooftop, and it's like, well, can I just be strapping this to the metal roof directly and not maintain that 1 inch clearance? Yeah, it's possible. You have to use thicker cable, because if you're putting additional temperature onto that cable and onto that conduit, you got to take temperature out somewhere. And so you take that temperature out from the cable itself by having less resistance in the cable, having a thicker cable gauge for the same amount of power. Neutral conductors do not count as current carrying conductors when making these ampacity derating charts. Your grounding cables don't count either. So now we're getting into cable jacket selection and ampacity rating based on what the ambient temperature actually is versus what the ambient temperature of the cable jacket rating actually is. And so what we're seeing here is that if the cable jacket is rated for 86 degrees Fahrenheit and it's operating at less than 50 degrees Fahrenheit, well then if we're using 30C, if we're saying all of our calculations are being done, based on a set 86 degree 30C temperature rating, but I then go and use 60C conductors instead of 30C conductors. They don't really make 30C conductors. What this is saying is, hey, I'm operating at less temperature than what my cable is rated for, and so it's actually giving me additional ampacity, 30% more additional ampacity. But if I go and I get right up to my temperature rating of my conductor, and I'm saying, okay, I'm doing all of this calculations based off a ampacity rating chart where the allowed ampacity is calculated at 30C, but my actual ambient is above that rating, then I'm having to discount my ampacity because my operating temperatures are beyond what the chart ampacity says. So you're going to get all these charts that say, well, if you're doing all your calculations at this temperature, use these ratings. If you're doing all the capacities at that temperature, use those ratings. And then you have to adjust for ambient temperature. So you say, okay, I'm doing all of my calculations at this temperature rating, but my actual ambient temperature is above that temperature rating. And so this is how I need to adjust the ampacity of my conductors based on that temperature rating. And what we see is if you're operating at higher temperatures than what the actual cable is rated for, it says, no, we're not allowing that. What we're allowing you to do is select cable jackets that are rated for even higher temperatures than what you're operating at. And if you're selecting at even higher temperatures than what you're operating at, well, then you might get some additional allowed ampacity. And so and I have to look at that number. That probably is a 1.09, not a 2.9. There's probably a typo there. But what we see is the ampacity, allowed ampacity numbers increase. The D rating is less the higher temperature the conductor is rated for. And so what we're saying is, okay, if I'm using 90C wiring and I'm operating in a 66 to 70C environment, but I go and I look up some tables in code and it's giving me an ampacity rating for this conductor, that table that's giving me the ampacity rating for the conductor is given at a particular design temperature. So to adjust from the table temperature to the actual temperature based on which conductor temperature rating I'm selecting, it'll give me different fudge factors to make my determination in. And so generally speaking, for solar, we're using all high temperature rated devices, and in some, especially if you're going within 1 inch of the rooftop and you're adding 60 degrees Fahrenheit to that adder. And so you're saying, okay, well, my ambient is 120, but because I'm within 1 inch of the rooftop, I have to add 60 degrees Fahrenheit to that. That's going to put my design temperature up to 180 degrees Fahrenheit. And the only way I can get there is to use high temperature rated cable. And so here's a chart for ambient temperature correction that's not the 30C 86 degree Fahrenheit. This is a 40C 104 degree Fahrenheit. But the table looks pretty similar. It's still giving you ambient temperature correction factors based off 90C wiring and the ambient temperature. The thing is, if I'm pulling from other charts to say this wire has 20 ampacity, I need to make sure that when I'm using that chart, that I'm looking at that chart's temperature basis and keeping like with like. If I'm using a 40C 104F Ampacity chart for my cable, then I can go do all my calculations for my temperature correction factors using this table instead of the previous. And what does that gain me? Well, if I'm assuming my base case is at a higher temperature, my temperature correction factors actually allow for a little bit more ampacity. But if you actually went and did all the calculations at a 84 degree Fahrenheit base case and used all the temperature correction factors for an 84 degree Fahrenheit base case and then adjust for the real ambient, you get to the same finishing point. And it's confusing because these temperature corrections at the tables that display the same information sometimes can appear a little bit later in code. So when you're thumbing through your code questions and you're looking up wire ampacities, you need to read the headings of the charts, because it'll tell you, if this chart was calculated, if the data was calculated using 104 as a base reference or 86 as a base reference. It's a little confusing until you actually do a calculation yourself and thumb through the books. But the general deduction for having more than one conductor in a conduit is, you would do that standard 25% oversizing just because that's the standard NEC. And then you have to go and say, what is my actual, temperature versus the design temperature, and derate it by that much. And then you have to say, okay, well, I have more than 3 conductors in a conduit, and I have to derate it by that much. And then that finally gets you your final design amperage. So, National Electric Code is a series of correction factors to say 25% is the base case, but now this is unusual. I have more conductors running through a conduit than I should. I need to adjust for that. I'm operating at higher temperatures than normal. I need to adjust for that. So you apply these additional correction factors into play. Normally with solar, you're not running into this at residential levels because you're already upsizing the ampacity of the system so much for voltage drop that you already have all this headroom built into your cables as far as ampacity to begin with. It's not like that in other industries. In other industries, they're usually designing the cable based on the amperage and kind of ignoring the voltage drop component. And so here we have I still don't know what's going on with this number here. I have to figure this one out. I still think that maybe these numbers I should be swapped. I'm not sure. It should be an increasing trend. But what we can see is that the temperature correction factors to say, at colder temperatures, if you're using this high temperature wire, you can have even more ampacity in them than, based off 104 basis versus an 86 basis. It's like, well, which basis do you use? The answer is it doesn't matter. You just have to stick with one or the other. Code is going to give you multiple charts based on that. Now, I would say in solar, generally, you're using just higher end charts on the temperature spectrum than otherwise. I didn't write the code. I wouldn't have all of these different charts in there, but they spend more time thinking about it than I do. And so there's, even in the headings of the charts, you'll have different temperature derates for charts in a raceway versus cables in free air versus cables kind of in windy environments. And so in a raceway versus in free air, you'll actually get more ampacity allowed in free air than you would in a raceway because of how that raceway encloses the heat and doesn't let it dissipate as much as free air would. And so, for example, here's an ampacity table. And it says, okay, for this ampacity table, we're doing it at assuming a temperature of 86 degrees. And so if I have number 10 copper at 86 degrees, if I'm using 140 degree cable, it's rated for 30 amps. And I'd say, okay, well, I'm not operating at 86 degrees. Up on the roof, I'm operating at 130 degrees or 190 if I'm adding 60 C to it. Then I go and use those ambient temperature correction tables based on whether or not this table, this 31015, if I'm taking the ampacity rating from the table that's done at 86 degrees or from the table that's done at 104 degrees. And what we can see is based on which table you're using, it's saying, okay, number 8, has a 50 ampacity rating at 86 degrees or a 57 ampacity rating at 104 degrees. Well, guess what? If you go and use the 104 degree ampacity correction factors, they're less steep of a discount than if you're using the 86 degree factors. And so, all across the board, basically what it's saying is, if you're using low temperature stuff and you're operating at higher temperatures, do all your calculations at this low temperature index, and then you're going to just have, when it comes time to apply the fudge factors, you're going to have harsher fudge factors. Or you can start out with a higher temperature design index and have lower fudge factors, but it's all going to work out the same at the end. And then what we're starting to see here is different kinds of cable jackets for different kinds of temperature ratings. So here we don't see this -2 rating, and here we do see this -2 rating. And it's kind of indicating that -2 rating is for higher temperature environments. In fact, the -2 rating is for sunlight exposure. So it says if you're building in a trench and you're spacing out all of your conductors appropriately, provided that you're applying by the enough spacing, then you don't need to reduce for conductors in a trench. But if the conductors were just thrown into the trench and not spaced out, then you would have to use the bundled conductor D rating. This is one of my favorite parts of code. There's so much to look at where all these cable jacket abbreviations finally begin to make sense. We got mineral insulated cable, which is a special tough cable that is often allowed to not be in conduit because it's so tough itself. Then we have just general kind of plastic cabling. There's RHW2 or THHN or THHW, and they're all different. THHN, you can find that in the store, and it does, if it's not cross-listed as THHW, then it's only allowed in dry or damp conditions, whereas THHW is allowed in wet conditions. That doesn't mean, THHW is still rated for inside of conduit. You might need a special cable that's rated for outside of conduit. So how do you be in a wet condition but inside of conduit? Oh, it's if the conduit is in a wet environment. If that conduit is up on a rooftop, the cable is still rated to must be inside of conduit, even though it's on a roof. Even though it's a wet condition and you have a wet rated cable, it still needs to be in that conduit. And the reason is its cable jacket is not as robust as conductors that can be, outside of conduit. So there's reasonings for that. It's a thinner cable. For that matter, you can fit more just plain old THHN into conduit than you can with THWN2 with well, THWN2. We're actually seeing this same conductor rating, but you can see how you get into THW2, you get into a thicker jacket, can't fit as many. PV cable is an even thicker jacket. More like underground feeder cable, like a 2 millimeter cable jacket. So you can't fit as many solar cables into conduit as you could THHN, nor should you, really, because that solar cable with its thick cable jacket that's rated for outside of conduit, it wants to be outside of conduit. You put it inside conduit, it's going to collect more heat. It's not a huge deal. Sometimes I'll take my solar cables and bring them straight into the attic and then transition to THHN for my home run if I'm indoor the rest of the way. But the point is that each of these terms has a meaning. Each of these cable jacket ratings has a temperature rating, and some, like THWN, are just rated for 75C, whereas THWN2 is rated at a higher temperature, and that means that when you get into extremely hot temperatures, there's going to be less amperage derating that you have to do for a 90C rated conductor than a 75C rated conductor. To the point where eventually your lower temperature conductors, they just flat out stop giving you derating numbers for much higher temperatures than what exceeds the jacket rating of the conductor. They say, no, it's not rated for this environment, so you can't use it, and we're not giving you a derate rating for it. Spacing requirements, in damp or wet locations, the boxes have to be off of the wall by 1/4 inch. You can't just flush mount a metal box to a wall in a wet location because it'll condensate on the inside of the box. So you need to have that air there. Spacing requirements between live parts and the face of the box. The conductors going into an enclosure, if you're splicing within a box, the conductors should not exceed 40% of the cross-sectional area of the box, and the actual splices and taps should not exceed 75% of the area of the box. So what that means is, like, if I have a box here, and I need to do some splicing, there's some splice taps that are like the size of a child's fist. And then one conductor might be going into there. The conductors can't exceed 40% of this area, but these little knuckles can't, just be stacked from wall to wall either. They have to be kind of the taps, the locations of the splices, the locations of the taps have to be spread out. And so in small conduit bodies, these are called LBs that kind of go in one side and out the other. You're not allowed to do splices and wirings inside these boxes because they're not large enough to contain the boxes and taps. It's not that you couldn't do splices in them, but by the time you look at the conductors in here and the size of those wire nuts and all that, this gets full up and you don't have that spacing inside them. So they just say, conduit bodies that contain wires that are less than number 6 shouldn't contain splices or taps or devices, even though you're allowed to put splices and taps and devices inside boxes. Just not when they get so full. Okay, solar has to be in metal, fully enclosed when inside a building. And so I really like MC cable. MC cable is this jacket is just twists of metal. You can actually physically unwrap it if you want to. It takes a while. This wrapping is not weatherproof for outside. Water can get into it. Now, sometimes you can get THWN to conductors inside the MC cable, and that's useful if I wanted to run this MC cable up through the attic, up into the rooftop, and then have my conductor peel back a little bit and have my conductors stick into a box up on the rooftop. So then I still have THWN2 wet rated conductors up in the box coming straight out of my MC cable. If the MC cable only has THHN conductors in it, you'd have to transition from those conductors into a box up on the rooftop, or just PV cable into the box in the attic and then straight up through the roof. So the question is, like, do you run metal conduit through the attic and then pull the conductors through the conduit, or do you get it pre-made? And so you can get this flexible metal as conduit, like they call it flexible metal conduit, or you can get metal cable. The metal conduit, the metal's empty and you have to pull the cables through. The metal cable, it's actual cable with a metal sheathing that's already pre-made up. And it costs an arm and a leg. $3 a foot for solar purposes. But it's so convenient because you don't have to do the cable pull and you can get it into, through an attic very easily. That it's very popular in solar installers. But you got to be aware that, some jurisdictions require additional cable jacket strength, which this wouldn't have. It's not wet rated, it's damp rated. And so when I have a house and I'm going through the attic, I'll take my MC cable sometimes. Instead of transitioning inside the attic, I'll just run it up into a box and then stick it out just a nub if it's protected from the awning. But then I'll put a box right, on the underside where it comes out the soffit, and then transition to EMT for my box-mounted inverter on the side of the building below. So in most projects, when you're doing DC through the house, MC cable is just the nice way to do it. It gets hot up on a rooftop. And so, the failure points on a roof and solar in an otherwise well-installed code-compliant system is if something gets into there where they shouldn't be. In Australia, they require disconnect switches, just like in the US, we require disconnect switches on the sides of the house. In Australia, they require them up on the rooftop. And these disconnect switches are bemoaned by installers as being a fire hazard, because every time you cut and splice a cable, that terminal point is where the temperature is, and there's been reports of debris and clutter leaves getting underneath the array, and the roof getting so hot that debris catches on fire, and the fire point turns out to be that rooftop isolator switch. The way you avoid that is you make sure your rooftop isolator switches are not, disconnect switches for indoor appliances or down on the ground appliances that have those 60C and 75C temperature ratings. You really want to make sure any kind of roof mounted boxes has a 90C temperature rating. Or if you're not going to do that, then don't do any terminations in these boxes and just have your conductors go straight into the box and then down into the attic, and avoid terminating on the roof. Now, in the solar industry, you buy specialty equipment boxes called a Soladeck that has the higher temperature ratings to do that, or you just go straight into the roof. Now with metal-clad cable, the only other thing is it's only allowed in accessible attics. So while it's great for attics, attics that are completely closed off and sealed off, it's not good enough. Finally, we get to what I don't like about flexible conduit, or conduit for that matter, is they do require just physically to bend a straight piece of metal to bend it 90 degrees. It requires some distance offset to make the bend. You can't just go with a harsh 90-degree bend of a conduit body. Now you can get a fitting, you can get an LB fitting that instead makes a harsher 90-degree conduit body, and it has a lid, and you take the lid and you pull the cable, and then you wrap it, do a little loop, and then you put it down in there, and you shove the loop into that conduit fitting box. As an installer, I don't like LBs because they're more difficult in most cases. But as a designer, they're preferred because the difference is conduit coming and making a big broad loop over the side of the building versus a nice tight turn. Your conduit fittings can hug the conduit a lot better.